I have the air conditioner on in the background. Hopefully that doesn't annoy you. All right, so we've been talking about big O, and it's the relationship, big O, okay, is the relationship, is the general relationship between the number of total things in the search space okay, versus the number of things you have to search through. Okay? And specifically what we're saying is if we call this 1 and call this 2, we say how does 2 change as 1 increases? Okay? And the way we do this, and the way we apply this, is we apply it to algorithms. So, in any specific algorithm. Okay. So far so good. That's what we've kind of done so far. There's an idea of for loops, and how they can give you a key, but don't be reliant on them. But how they can give you a key to how complex a given algorithm is. And by complex, we mean the big O, right? The worst case scenario and upper bound of runtime. The order of the relationship between the number of things in the search space being increased and the number of things you have to search through. How does that increase when number 1 is increased, right? The number of things in the search space is increased. Okay, so let's say we have linear search, right? And so we have this idea that we want to go through an array of any size and find some sort of target values in there. So we say something like, and we do the Boolean version of this. It doesn't matter. We can do the index version too. Linear search, right? And we have our array and our target value, okay? And we have an algorithm that works, right? It's an algorithm, so it works for any sized array and any target value, all right? It's able to determine that. How do we do it? And we've developed this algorithm before. We say, okay, well, arrays and for loops have this intimate relationship. If we want to traverse through an array, we use a for loop. And so we could say something like for int I equals 0, I is less than the length of the array, I plus plus, and then whatever we do down here, right? If at the certain bucket it's equal, etc. Okay? Now, the length of the array, as that increases, right, the number of things we have to search through increases linear, right? We looked at that already. And so people will look at this and they'll immediately say, well, this is a for loop and it depends upon length. And so if you see this, this tells you that it's an O of n algorithm, okay? Or to put this another way, if I say instead of length n, right, then as n increases, the number of times I go through this for loop to find the target value increases linearly, and I'm going to say it's O of n, okay? And then people will also say this kind of thing, okay? All right, so we talked about this, right? We talked about, I don't know, we had a length of n, and we have a length of n plus m. Now we have 2 degrees of freedom, okay? That means 2 different things can change, all right? And in this case, these things interact with each other, okay? You can't change the number of rows without changing something in the columns. Okay, right? So if we add a new row, we're adding an extra square to each column, right? And vice versa. And if we want to traverse through all this, well, we kind of talked about it already, right? You did it in the TV exercise where you said for int I equals 0, I is less than our length, or I is less than n, I plus plus, and then we can say, so we're going through each row, and now we have to go through each column for int r equals 0, r is less than n plus m, where m is any constant, okay? Can be any constant you want, okay? R plus plus, and we play this game again, okay? So this is on the scale of n, okay? It's dependent on n, all right? And this is dependent on n too, all right? And the way we figure this out, how many times we have to go through this inner loop, okay, is we say, well, we're going n plus m times through this inner loop and n times through this outer loop, so n times n plus m, and we say that's n squared plus nm, right? And we're taking the order of this thing, so we don't worry about anything except for just the coefficient, or not the coefficient, the power of n, okay? And in that case, this thing is O of n squared, okay? And so people will see these nested for loops and be like, okay, well, that tells me that maybe it's an O of n squared algorithm, all right? And the same thing happens with the triple nested for loop, right? So if I'm doing just real quickly, if I'm playing this game with, you know, a movie now, right? Then I have for the movie, for each movie, okay, for each row, for each column, do something, okay? At that point, we're at a triple nested for loop. All right, we have 3 degrees of freedom, and all 3 of those degrees of freedom are being multiplied here, so we get O of n cubed, okay, will be our relationship. And you could say like, well, I'm going to call one n, I'm going to call the other one n plus m, I'm going to call the other one n plus z, where m and z are constants. Okay, whatever, it's still going to be O of n cubed, right? Because we're looking at the biggest value of that. So, all right, so you kind of get it. You're like, okay, well, every time I nest a for loop, there's another issue. It's just adding another n. Not true, right? The degrees of freedom are an important part of this, okay? So let's say that example earlier where we have red, green, and blue, okay? So we have RGB values in one line of pixels, okay? So we have an RGB value here and an RGB value here, and we have to look through RGB in all of these, okay? So you're thinking, well, for, and we say the length of the array. Why don't I just do it so you don't get confused? Int I equals 0, I is less than the length of the array, I plus plus, and then we want to go through each of these values, R, G, and B, and so you say something like for int P equals 0, P is less than 3, because you're going through 3 values, P plus plus, okay? Now, this is not a degree of freedom, okay? Because no matter what, no matter how many times we change n up here, this stays at 3 and will always be 3. It'll never be 2, and it'll never be 1, and it'll never be n, and it'll never be 15, and it'll never be anything. It's always 3, okay? So what this ends up being, and I'm going to change length to n up here, right? That's kind of what we did last time. So if you look at this, you might say, oh, nested for loop of n squared. Not the case. What it really is it's 3 times n, right? We have 3 down here and n here, and so we multiply them out, and 3 times n. And that means the order of this is O of n, right? We just grab this and put it in there, okay? So we've done O of n squared, O of n cubed, okay? And we'll do one more, and then we'll look at some of our sorting algorithms and classify them.